Okay, so this is going to be the second video with the bottom problem that we didn't even start in class. So it's very similar to what we did in class, but there's an added piece here. P of x is defined as 5 plus the integral from 6 to x of f of t dt. Now in this graph I didn't forget, and I actually have the graph of f, so this is the graph of f of x. And P of x is defined from -3 to 15 as the net area under that curve plus 5. Notice the plus 5 is outside of the integral, so you can't bring it in. It's a separate piece to the function. The first question says to compute P of 6. Well, I'm going to go ahead and plug everything in. I'm going to copy my function just as it is, so I still have a 5. I'm going to add the integral from 6, and instead of x, I'm going to put 6. And then I'm going to put f of x dx. And what you're going to notice right away is that property, the integral from 6 to 6, is simply going to be 0. So this whole thing goes to 0. Another way to think of it, if you're not moving in any direction, you're not covering any area, so that's just 0. Then I'm going to add 5. So in the end, P of 6 is going to simply be 5. So all that happened with the 5 is once I computed the integral, I added 5. That's it. The next question asks for P prime at 6. So that means we're going to have to come over here and we're going to have to take the derivative of this. Well, let's go piece by piece. I'm first going to take the derivative of 5. So that means P prime of x is going to be the derivative of 5. That's a constant, so I'm just going to make it 0. Plus the derivative of the integral, which we know cancels, and then I plug in my x, so I get f of x. So although the function looked a little bit different than the previous example, in the end, P of x is still just f of x. And so when I go ahead and try to find P prime of 6, try to do it up here so I don't run out of space. P prime of 6 is simply going to be f of 6. So I'll go to 6 and I'll find the corresponding y value, and that of course is 3. So that's 3. Now it wants P double prime. So if P prime is f, then P double prime is going to be f prime. Basically, think of it as taking the derivative of both sides in this equation. So then if I want P double prime of 6, I will have to find f prime of 6. Okay, just a moment. There we go. So now I'm looking at a slope. This one, the f of 6, I was looking at a y value. Now I want a slope. So if I go to 6, the slope there is we have a horizontal tangent line, so the slope is 0. So I get a 0 for an answer. And they're going to be really strategic if they ask a question like this, because if I had done a slope at 3, that would be hard to calculate unless this were a line of some sort. So they're going to be real strategic so that you can find the slope given the graph. The second question says to write the equation of a tangent line. So we already know that we need a point. The first point is 6. And you need a slope, and the slope is given by the derivative. So P prime of 6. If I find the y value, I think I've done that already. Oh yes, that's right here. P of 6 is 5. P prime of 6 is 3. Found that here. So I just set that up as y minus 5 is equal to 3 times x minus 6. And I have the equation of my tangent line. All right, on what intervals is P of x decreasing? Decreasing means P prime of x is going to be less than 0. Okay, that's from the last unit. Well, P prime of x is equal to f of x. So the real question is, when is f of x, the function they gave us, when does that live below the x-axis? And so we're going to go from -3 to 0. Again, increasing, decreasing will accept parentheses or brackets. So in this case, I'll go -3 to 0. And there's another spot. It's going to be 12 to 15. Okay, I think in class we had used a bracket on one of them because here it is negative and here it's 0. But it's decreasing. The question is not about when is P prime of x negative. The question is decreasing, so we'll accept both brackets or parentheses. Just make sure that they're the same. And I didn't do that in, I think, second period today. On what intervals is p of x concave down? Well, concavity, as you saw in the last example, is related to second derivative. So this means second derivative less than 0. So let's see. If we take the derivative of both sides, I get p double prime of x will then equal f prime of x, which we are looking for being less than 0. Let's see. Okay, sweet. So then I will look for where the slope is negative. So these were y values. This is going to refer to slope. And of course, that's when the function is going down. So we're going to start going down at x equals 6 all the way to x equals 15. So 6 to 15 is the answer for the concave down part. Then it asks about inflection points. Inflection points are changes in the concavity, which means the second derivative is going to change sign. And for us, we're looking at the slope here. So we need to figure out where the slope of f is going to change direction or change sign. So that's going to happen at exactly x equals 6. So my inflection point happens at x equals 6. And I was only asked to give the x coordinate. All right, maximum and minimum. Well, if we're starting at, the function says to start at 6 and then add 5. Let's go ahead and start at 6. And everything is going to be added to 5. No matter where you stop, you add 5. So that 5 is really going to just be the same for any x. So you can, the max or the min is really going to be determined by the net area. If we move to the right, all of this area here will be positive. And then here it's going to become negative because you're below the x-axis moving to the right. In contrast, if we go to the left, this area is above but moving to the left, so that's negative. And then you get a double negative here. You have a negative position and a negative direction because we're starting at 6 and moving out to negative 3. So that makes this positive, the double negative. Well, area is cumulative. So that means, hey, if I start at 6 and I move to the right, I'm going to get a bunch of positive. But as I keep moving, that positive area is going to get canceled with some of this negative. So clearly the area at 12 is going to be higher or bigger than the area at 15. If I go to the left, I'm going to have a bunch of negative area. And then if I add a little bit, it's not going to make it positive. So clearly the most positive area that I get happens when x equals 12. And the minimum value, which is the least positive area or the most negative area, is going to happen when I go to the left, but I have to stop at 0. If I keep going, it's actually going to cancel some of that negative out, and it make it so that it's not at, it's a number that's less negative. That sounds funny. Anyway, so x equals 0 is when is the x value where I get my minimum. Now, both of these can be answered in a table like I explained in the other video. So I'll go ahead and do that. I will set up my table x, p of x. Okay, and then I will put my endpoints, which is negative 3. And then I will put positive 15. Whoop. And then I will do critical points. So I will say I need when p prime of x equals 0. So that's when f of x equals 0. And I get 2 CPs. I get one at 0. And I get one at 12. But here's the trick. I can't really find the actual area here because this is a curve. So the only thing I could do is approximate it. So we're just going to take a look at this kind of like eyeballing it. If we go to 0, we're going to get a negative area. If we go to negative 3, we're going to get less of a negative area. If we go to positive 12, we're going to get a big positive area. And then we're going to get less of a negative if you keep going. So in this case, it didn't work better than just using like logic graphically. In the previous one, it worked out nicely because we were able to compute it given that the graph was lines. So there you have it. Example number 2. Hopefully this helps with your worksheet. See you soon.